Okay, today we're going to go over homework problems from chapter 18, which is the chapter on electrical charge and electrical fields. And there are just a couple of equations that you just need to basically remember in order to do these problems. First thing I'll point out is the charge equivalent of a single electron is 1.60 times 10 to the minus 19 coulombs. And coulombs is the Systems International unit for electrical charge. And so the reference value, or the standard value for charge, is equal to 1.6 times 10 to the 19 coulombs. And that's minus for an electron and plus for a proton. So that's one equation. The second equation is that the force that's generated by two charged particles is equal to a constant times the charge on the first particle in coulombs times the charge on the second particle divided by the distance squared between the two. So Q1 is equal to the charge on the first, Q2 is equal to the charge on the second, and both of these need to be expressed as coulombs. So for example, if you're given that the charge is 2.00 microcoulombs, then you need to, what you put in here is 2 times 10 to the minus 6 coulombs. R is the distance between them in meters. Very important that it's in meters. And that's because the constant is 8.99 times 10 to the ninth. And it's newtons per meter squared, coulomb squared. I think that's right. Something like that. It has to be in coulombs and it has to be in meters in order to use this constant. The other formula that we'll be using today has to do with an electrical field. And there's actually a couple of these. The electrical field generated by a point is equal to the absolute value of the charge divided by the distance from the field at any point is equal to the absolute value of the charge of the field, charge of the particle. That's also in coulombs. R again is the distance in meters, and the constant is this constant again. Now since there's one Q missing here, the field is exerted on a particle based on its charge. So that, the force that's exerted will be based on the charge of whatever wanders into the field. Okay, with that little introduction, let's get started. The first problem is problem number 2. Problem number 2 states, if 1.8 times 10 to the 20 electrons move through a pocket calculator during a full day's operation, how many coulombs of charge move through it? Now basically this is a conversion. What you want to do is you have 1.8 times 10 to the 20 electrons, and that moves through a calculator in one day. And what they want to know is, what is that in coulombs of charge? And so basically we know that one electron is 1.6 times 10 to the minus 19. And so you just multiply these two together, and it gives you the answer, which in this case is 28.8 coulombs. And because this is an electron, then this answer is negative. So that's number 2. Number 4, a certain lightning bolt moves 40 coulombs of charge. How many fundamental units of charge, that is QE, is this? So you have 40 coulombs of charge. So how many fundamentals is it? And so you're going to take 40 coulombs divided by 1.6 times 10 to the minus 19 fundamentals, so QE coulombs per QE, I guess would be the right way to say it. And so you end up with, if you divide that, you have 2.5 times 10 to the 20 fundamental units, or electrons, or well, it's lightning, so it's probably not protons, but so you have 2.5 times 10 to the 2.5 times 10 to the 20th fundamental units. Number 6. Number 6 states an amoeba has 1 times 10 to the 16 protons and a net charge of 0.3 picocoulombs. So it has 1 times 10 to the 16th protons and a charge of 0.300 picocoulombs. Now, pica is 10 to the minus 12. And so this is 3.00 times 10 to the minus 13 coulombs. And the question is, how many fewer electrons are there than protons? And so the charge, 3 times 10 to the minus 13, and you divide that by the fundamental, there's 1.6 times 10 to the minus 19 fundamentals, or C per fundamental. So the imbalance is going to be this division, which is 1.87 or 88, we'll say, times 10 to the 6th fundamentals. Or there are that many more protons than electrons. Well, it depends on if this charge is saying it is that this charge is positive, so it's protons. B states that if you paired them up, what fraction of protons would have no electron? So you have 1.88 times 10 to the 6th fundamental charge units, and the total number of protons is 1 times 10 to the 16. So the fraction that is unpaired is 1.88 times 10 to the minus 10. Okay, number 7. A 50-gram ball of copper has a net charge of 2 microcoulombs. So the charge here is 2 microcoulombs, which is 2.00 times 10 to the minus 6 coulombs. And you have 50 grams of copper. What fraction of copper's electrons have been removed? Well, you need to know the total number of copper electrons and then what this represents in terms of fundamentals. Okay? So the total, first of all, you have 50 grams of copper. And hopefully you remember that 1 mole of copper is 63.4 5 grams, and you have 6.02 times 10 to the 23rd atoms per mole, and then the atomic number of copper is 29, and so you would multiply that by 29 because every atom has 29 protons. So that's one atom. And if you do all of that, you end up with a total of 1.37 times 10 to the 25 protons or electrons. If there was no charge at all, then you would have this number, okay? But now you do have a charge of 2 times 10 to the 6 minus 6 coulombs. And you know that 1.6 times 10 to the minus 19 equivalents, or coulombs per equivalent. And so that means you have a total of 1.25 times 10 to the 13 unpaired equivalents. So that number of unpaired equivalents divided by the total tells you the fraction that is unpaired. And so that's 9.09 times 10 to the minus 13. So that is the fraction of unpaired protons you would have to have in order to have this charge. That's a large number of unpaired electrons, but there's a huge number. That's what makes the fraction so small. Number 9. If you have, how many coulombs of positive charge are there in 4 kilograms of plutonium, given that its mass is 244 and that each plutonium atom has 54 protons? Okay, so you have 4 kilograms or 4,000 grams of plutonium. 1 mole of plutonium, as it says, is 244 grams. And there are 6.02 times 10 to the 23rd atoms per mole. And it tells you that there are 94 protons per atom. So if you multiply that whole thing out, you get 9.28 times 10 to the 26th protons. And if you multiply that by this charge per proton, or per equivalent, then that will give you the charge, which is, if these were all unpaired, it'd be 1.48 times 10 to the 8th coulombs. A huge charge if they were unpaired. Let's do one more. And with this one, we're moving into our next group, which is the force, or Coulomb's law. What is the repulsive force between two pith balls that are 8 centimeters apart and have an equal charge of minus 30 nanocoulombs? So Q1 is equal to Q2 is equal to minus 30 nanocoulombs, which is the same as a minus 3.00 times 10 to the minus 8 coulombs. R is equal to 8 centimeters, which is equal to 0.08 meters. And then we know that K is 8.99 times 10 to the 9th. So F, which is what we want, is going to be K Q1 Q2 over R squared, which is equal to 8.99 times 10 to the 9th, times 3.00 times 10 to the minus 8, and we'll just square that since they're both the same, divided by 0.08 squared. And if you do all the math around this, you get 1.26 times 10 to the minus 3 newtons. And that's the force that's generated between those two pith balls. Now, if they're both negatively charged, then it will be repelling. They will repel each other with that level of force.